So, in the last lecture we looked at couple of examples of quadratic fields with class group isomorphic to Z mod 4Z. We will continue looking at these examples in today's class also of quadratic fields, and we will compute some more class groups. It brings together everything that we have learnt in this course, computations of rings of integers, discriminant, computation of factorization of prime ideals, and computations of the group of units, and put it together to compute the class group. So, these are nice examples. It kind of brings the course together in a very nice way. So, let us look at examples, a few more examples today. So, first one is q square root of minus 30, right. And so, minus 30 is not congruent to 1 mod 4 obviously, and so discriminant is minus 4 times 30, which is minus 120, and so Minkowski bound is 2 factorial by 2 square times 4 by pi times square root of 120. Square root of 120 is very close to 11, and so this is if this is sort of less than 22 by pi, and if you really sort of, rather than approximating pi by 3, if you do approximate it by the more well known thing, which is 22 by 7, you get sort of 7 by 22, and so this is this is roughly like 7, right. I mean, this is exactly 7, but the first thing is rough. So, so anyway, the Minkowski bound is less than 7. So, ideal class group of K is generated by primes dividing 2 OK, 3 times OK, and 5 times OK. So, we have to find the prime factorization of these things, right. So, the polynomial that we consider is this one, and so 2 times OK is P2 square, 3 times OK is so 3 also divides the discriminant. So, this is P3 square, and 5 also divides the discriminant. So, this is P5 square, right. So, each of these P1, P2, P3 and P5, so CLK is generated by P2, P3, P5, and each of them has it satisfies PL square is 1 for L equal to 2, 3 and 5, right. So, they are all possibly of order 2, they could be of order 1, we do not know, and there could be relations amongst them as well, right. Okay. So, how do we show whether, so okay, so if PL is equal to A plus square root of minus 30 times B, L is 2, 3 or 5, then A square plus 30 B square is equal to plus or minus L, right, and minus L, of course, this has no solution. So, plus L, right, and they have no solution. So, this has no solutions, okay. So, none of P2, P3, P5 are principal, but that does not mean that they can't have relation between them, right. So, so that can of course happen. So, what you do now is you so for example, you could take something like square root of minus 30 itself. So, you consider norm of square root of minus 30, and this thing of course is just 30, right. Right, which is 2 into 3 into 5, right. So, hence if you take the ideal generated by square root of minus 30, this will be P 2 times P 3 times P 5, right, which means that P 2 into P 3 into P 5 is 1. So, there is some relation between them, right. It is not a it is not like there is no relation between these two. So, now we want to find out whether there is a relation between P 2 and P 3, for example. So, we consider P 2 times P 3. If this were alpha for A plus square root of minus 30 times B, then we would get that A square plus 30 B square is equal to 6 or plus or minus 6, right. And this has no solution either. Okay. So, hence that is kind of enough to say that there is no other relation between P 2 and P 5 either, because if there were some relation between P 2 and P 5, then we would be able to write P 5 in terms of P 2, and then we would be able to write a relation between P 2 and P 3, and similarly between P 3 and P 5. So, hence the ideal class group of K is isomorphic to Z mod 2 cross Z mod 2, Z mod 2 Z cross Z mod 2 Z, right. So, here we have and they are generated by, so you could take this copy to be generated by P 2 and the other copy to be generated by P 3, and then P 5 is the, so is corresponds to this 1 comma 1, for example. Okay. So, let us look at some more. So, the next one is kind of somewhat intricate because it is real quadratic field, right. And as I said at the beginning of this lecture, real quadratic fields are usually more difficult. Okay. So, so 79 is not congruent to 1 mod 4, it is 3 mod 4, right. And so, the discriminant is 4 times 79, which is 316, right. And so, if you look at the Minkowski bound, this is 2 factorial by 2 square times square root of 316, which is square root of 316 by 2 minus, so 18 square is 324, which means that this is less than 9. Okay, this is less than 18 by 2, which means that it is less than 9. And so, I need to, so class group of K is generated by prime factors of 2 times OK, 3 times OK, 5 times OK and 7 times OK. So, you also have to factorize a lot of things. All right. So, and what is the polynomial that we consider? The polynomial that we have to consider is x square minus 79. So, what is 2 times OK? I mean, of course, 2 ramifies. So, this is P 2 square, 3 times OK, this is, so 3 does not ramify, x square minus 79 is congruent to 78 is divisible by 3. So, x square minus 1 mod 3. So, this is P 3 into P 3 prime and 5 times OK. So, x square minus 79 is congruent to x square minus 4 mod 5, which is again reducible. So, this is P5 times P5 prime, and 7 times OK, this is x square minus 79 is congruent to x square minus 2 mod 7, but 2 is a square modulo 7. So, this is congruent to x minus 3 into x plus 3, right. So, this is again P7 times P7 prime. Okay. So, the class group of K is generated by P2, P3, P5 and P7. So, we would like to know if any of these are actually trivial, because each of them so at least P2 square is 1. So, so is P2 sort of A plus square root of 79 times B for some A and B. So, this means that A square minus 79 B square equal to plus minus 2 should have a solution, but this does have a solution. You can take A to be 9 and B to be 1, right. And so, P2 is 9 plus square root of 79, yeah, it is generated by this, right. And so, P2 is in fact just 1. There is no element of, this is not an element of order 2, but an element of order 1, right. So, that is why it is important to keep checking whether things that you have are principal or not. Okay. So, CL of K is generated by P3, P5 and P7. Now, of course, there could be some of these could be trivial, some of these could have relations amongst them and so on. We have to find out what's happening exactly. Okay. So, what we are going to try to do is look at lots of examples then of norm from, so let us look at 8 plus square root of 79. What is this? This is 64 minus 79, which is minus 15, which is minus 3 into 5, right. And so, we can rearrange these things and assume that this thing is P3 times P5, right. So, so P3 is P5 inverse, right, and norm of 10 plus square root of 79, this is 100 minus 79, which is 21, which is again 3 times 7, right. And so, so now we have already done our rearranging for P3 and P5. So, now, so this means, so we can't rename P3 and P5 now. So, in particular we can only say the following. So, this is P3 times P, we can rename P7 though, or it is P3 prime times P7. Okay. So, P3 P7, this is either equal to P3 inverse or it is equal to P3 prime inverse. Yeah. So, it is one of these. Yeah. So, more elegant way of writing this is it is either equal to this or P3. Anyway, we do not really bother too much about this at this point. Yeah. Okay. but we are going to do the following. We are also going to look at norm of 5 plus square root of 79. So, what I am doing effectively is just writing down lots of norms and then observing various things. So, this is 25 minus 79. So, this thing is 54, which is 2 into 3 cubed, and so maybe I will rearrange rename it at this point. So, forget about the previous thing that I said, and I rename so that this becomes P2 times P3 cubed. Okay. So, this means that P3 cubed is equal to is 1 in the class group, right, as P2, the class of P2 is already 1, we know that, right. Okay. So, this means that P3 prime is equal to P3 square, right, because it is inverse of this. Okay. So, this means that P3 is 1 or order of P3 is equal to 3. It can't be anything in between, right. P3 cubed is 1. So, either it is trivial itself or its cube is 1. So, anyway, what we have shown in the end is that the class group, so hence class group of K is generated by P3, and so so class group of K is same as is trivial or it is Z mod 3Z. So, we have to find out which one it is, right. So, let us say P3 is A plus square root of 79 B, right. And so, we would like to know if this has a solution or not, and again it is not going to be entirely straightforward. So, let me call this alpha, and so the ideal generated by alpha cube is same as the ideal generated by p cubed, but we know that this was the ideal generated by 5 plus square root of 79 times the inverse of the ideal generated by P2, which is 5 plus square root of 79, 9 plus square root of 79 inverse, and if you compute what this thing is, it becomes okay, let me do this. So, 5 plus square root of 79 into 9 minus square root of 79 by 81 minus 79, which is 2, and so if you do this you get 45 minus 79 plus 4 times 79 by 2, which is minus so 29 plus 5 is 34. So, minus 17 plus 2 times 79. So, it is in the ring of integers as you would expect it to be, right. So, maybe I should put all this in the bracket so that I am taking ideal generated by these. Okay. So, I get alpha cubed is equal to the ideal generated by this is equal to the ideal generated by minus 17 plus 2 square root of 79. So, alpha cube is minus 17 plus 2 square root of 79 times u for u in OK cross. Okay. And now what happens if I multiply u by something? So, by a cube. So, if I change if we change u by u times v cube for some v in OK cross, then we simply change alpha by alpha times v inverse or alpha times v, right. We can do that. And so u, so only, I mean u does not matter up to cubes, right. So, yeah, so u belongs to OK cubed modulo OK cross cubed. But what is OK cross? This is generated by yeah, okay, let me, this is epsilon. So, this is plus minus epsilon to the z, where epsilon is equal to 80, not 18, 80. So, here is a fundamental unit that is kind of not entirely trivial to find. You have to do some, you have to go up to 9 to get the fundamental unit. But this plus minus 1 does not make a difference, right. So, minus 1 is also a cube. Okay, so OK cross modulo OK cross cubed, this is 1 epsilon epsilon square, that is all, right. And so, what we do is we just compute this. So, so minus 17 plus 2 square root of 79 times times epsilon, this turns out to be 62 plus 7 times square root of 79. You can instead of this you can use epsilon inverse. So, let me do that, epsilon inverse. So, minus 17 plus 2 square root of 79 times epsilon inverse, this turns out to be, it is just a computation that you do, 2782 plus 313 square root of 79, right. And so, we want to solve for alpha cube is equal to minus 17 plus 2 square root of 79 or or 62 plus 7 square root of 79 or minus 2782 plus 313 square root of 79. So, how do we show that none of these are a cube? So, let me do it as much as I can. Right. So, what is, so alpha is a plus b square root of 79. So, alpha cube is a cubed plus 3 times 79 times a b square plus b 79 b cube plus 3 a square b times a square root of 79, right. Yeah. So, now you see that norm of alpha is equal to is equal to 3, and so this is a square minus 79 b square. So, a and b, they are both non-zero, right, and so therefore, Yeah, therefore, B times 3a square plus 79 b square, this was the coefficient of square root of 79 here. This must be at least 3 plus 79, right, which is 82, right. So, alpha cube is not equal to minus 17 plus 2 square root of 79 or 62 plus 7 square root of 79. On the other hand, if alpha cube is equal to minus 2782 plus 313 square root of 79, then b 3a square plus 79 b square is equal to 313. This is a prime number, right. So, hence b is equal to 1, right. I mean this thing is not, the thing in the bracket is at least 82. So, that can't be 1. So, the only thing remains is b is 1. So, you get 3a square plus 79 is equal to 313, and so you get 3a square is equal to or you know directly a square is equal to 78, which has no solution, right. So, that is how you, so it's, you see it's a lot more involved than doing computations for imaginary quadratic field, but this is how you do it, you know. I mean so here we have used the concept of size to get something, and this is an advantage of working in the real fields, where you can, there is a good notion of size, and it comes in handy often. Okay. So, in the next lecture we will look at a couple of more examples and learn a few more techniques on solving. Yeah. By the way, so I did not finish it quite here. So, this means that the class group is isomorphic to Z mod 3Z, right. I think that is yeah, okay. Yeah, so next time we will look at a few more examples of computations of class group. Thank you.